Are you doing videos for Science 20?
No. Chem 20, Chem 20, and Chem 30. I thought recording 3 or 4 videos in a day would be a nightmare. I don't know if my phone would last that long, and I don't want to have to deal with uploading that many videos.
Charge station right beside your phone.
I know. Well, that's
I'm fine. We'll learn about it. Okay, good. I was like, we have a
It's really ready.
probably like
why is this going
Nicole.
Already got rid of the show.
yeah, I wanted to give it to you really early.
I'm more she flex more than I have flex on. I have more than 8 on second.
Thank you. Like someone who's don't
You're losing at virtual beer pong. You'll win. You'll win at virtual water pong.
There's no water.
No, Kool-Aid pong, bro. Just cups. Don't worry about it. Okay, I handed you 2 different things. That is not enough. How many? Yes. So if you ever lose the video, just watch the video. They should be up before like 6 p.m. most days, but sometimes they're not. Okay, listen up. I've already 2 tests. They're on Power School. Some, like as with every test, some people do well, some people do not so well. We are a third of the way through our semester. We're two tests deep, right?
I think you marked the test wrong.
You think I marked the test wrong? I super didn't. I even checked some people's answers for certain questions, and
So what if they got it wrong?
if they got it wrong, they got it wrong.
Yeah, but then it's the correct answer.
Yeah, but I didn't get it wrong. Other people got it wrong.
What if they got it right? You did. So you use other people's answers for the answer.
No, never mind. Don't worry about it. So what I did want to say is that because we're 2 tests deep into this course right now, really we've only tested kind of 1 unit, right? We've only tested equilibrium. Okay, so I want you to understand that because it's a third of the course, but it's only 1 out of our 4 units technically, I need you to understand that there's lots of other places that you can still pick up marks in this course. There's lots of other places and ways for us to be able to do better. And remember that before we go into our Christmas break, everybody gets 1 rewrite, right? Before we go into our Christmas break. So that's kind of nice. It means lots of marking from you over Christmas or whatever. The exam review sign-up sheet is on the board. It's below the 2 pink pieces of paper. I'm restricting. I almost died the last time we did review because it was like I was going solid for 7 hours in a row. I was teaching and then I was reviewing and teaching and reviewing and teaching and teaching, and I didn't get a single break during the day for like 6.5 or 7 hours. So I'm restricting it now to only lunch times because I want to be available at Flex for other people, my Chem 20s and my Science 20s and stuff like that. So the review session is posted up there. Let me know. If you can't make any of those review sessions, you can always let me know, and then we can just review sometime outside of the timetable, right? That's totally fine too. I gave you the review booklet. So boom, day 1, you have the review booklet. You can kind of know what the expectation is for the exam that we're going to have in like 2.5 to 3 weeks. Okay? So let me know. We're starting. It's weird. This is chapter 13. So normally we would start with 13.1, right?
Yeah.
But that's not what we're going to do.
We're going to pull back.
Yeah, we're going to start with 13.3. Now, I need you to understand, like, this part, the first, like, 2 slides, the first 2 slides are really from the 13.1 section in our textbook. But we're going to do 13.3, and then we're going to go back and do 13.1, and then we'll do something else, okay? Yeah, and then we'll do 13.2, and then we'll do 13.4. So, but as long as you understand, you know, based off of the review booklet, you'll understand what the expectations are for each section in our notes and things like that. So hopefully we'll be okay. Anybody have any questions just straight out of the gate? We haven't even talked about anything, just straight out of the gate. Anybody have any questions? Shohei, that's a question for the ages, man. Talk to me about that later. Okay, let's grab our notes then and let's start talking about it. So this unit is all about redox. Now redox is 2 words put together. It's reduction and oxidation. So historically, the term oxidation has referred to when metals react with oxygen or water to form compounds, and reduction was a process where metals were produced from compounds. The production of metals from compounds is also called, and I really hope I don't spell this wrong, hey, there we go, metallurgy. So you're making metals from compounds. And so a pretty good example of that is like here when I take iron 3 oxide and I react it with carbon monoxide. When I do this is a process called smelting. It's a specific metallurgy process. I can get 2 irons for every Fe2O3 that I put in, and I get a bunch of carbon dioxide out. Now, what I want to get you to think about is here we got a gas and here we've got another gas. What I want you to think about is, what do you think would weigh more? Do you think this would weigh more, or do you think this would weigh more? The Fe2O3 or 2 Fe's? What do you think would weigh more?
Fe2O2.
Why Fe2O3?
Yeah.
Or why 2 Fe's? I don't know, Max?
The gas is pretty light, but it's still something.
Yeah, okay, so are you talking about this gas, or are you talking about the oxygen combined?
Oxygen
The oxygen combined with it, right?
Yeah.
We could actually figure out what the molar mass of this thing is, and we could figure out what the molar mass of this thing is and just multiply it by 2, right? And so we would totally get that this weighs more than that. And so what are you doing to the weight of this thing as you react it? You're reducing the weight of this substance. Does that make sense?
Yes.
So this is the traditional definition of something that we call reduction. Does it make sense why way back in the day, before they learned about, molecules and particles and things like that, does it make sense why they would call this reduction? If you started with, 30 pounds of iron oxide and you smelted it, you could get out like 20 pounds of iron. But you're always reducing the weight whenever you're doing this. Okay, this thing, what do you think's happening here? Are we reducing the weight by going from magnesium to magnesium oxide? No, this is oxidation. And what's another way that you know that this is oxidation? It's reacting with oxygen, so it's being oxidized. That's a traditional definition of oxidation. What about the last one? Is it reduction or oxidation? Both. Is this thing, is the nickel oxide, the nickel 2 oxide in here, is it being reduced or is it being oxidized?
It's being reduced.
This thing is being reduced, right? Now, that's a traditional definition of oxidation and reduction, Sanjana.
So would a formation reaction and a decomposition reaction kind of go hand in hand with these, or no?
You could, in a sense, if you could take iron 3 oxide and you could just decompose it without any carbon monoxide there, if you could decompose it to be iron and oxygen, that would be a definition of reduction, right?
Yeah.
Because you're reducing the weight of the iron ore. Yep. And a formation, if you took, like this is the magnesium plus the oxygen and you're making magnesium oxide, that's a formation reaction, but it also fits the definition of oxidation. So if you're happy with that, then I'm happy with that.
Okay.
But that's a traditional definition. We're going to move on from that in a second. Max.
If you look at the oxygen in there, reacting with the hydrogen to make water.
Yeah.
Is that considered an oxidation?
But are you reacting the metal? Is the metal reacting with oxygen or water?
Okay.
The metal is not reacting with oxygen or water. It's a metal oxide, so it's not a metal technically, right? This is an ore, this is a mineral. So the metal oxide is reacting with water to make, or reacting with hydrogen to make water. So it's almost like the reverse process. If you took the nickel and the water and reacted them that way, that would be oxidation. But the reverse is reduction.
Right. Thank you.
Good. Hey. Okay, so that's the historical definition of those things. There's like a 3% chance that you will be tested on that on the diploma. There's a tiny, tiny, tiny little chance, but there's a chance. So I need to tell you about it. We need to go over that. Now that is not the modern definition. The modern definition of oxidation and reduction is that a substance, if it's losing electrons, we call that oxidation. If a substance is gaining electrons, we call that process reduction. And there's a way for you to remember that. Has anybody ever?
Leo the Lions is good.
What he said.
Or oil rig.
Or oil rig. Where'd you learn that?
Burn the Lion.
Yeah, where'd you learn that?
Bio.
You learned that in bio, right?
Yeah.
Is that, I didn't know, because you have to do oxidative phosphorylation in biology, right? Like ATP and stuff like that.
Yeah. That one.
The oxidative phosphorylation, there's like a glassy stare. It's like ATP.
Yeah.
Oh yeah. NADP, NADPH, and stuff like that. Yeah, you know. Yeah, classic. Okay, so let's try this. I don't like the oil rig one because oil rig leaves out the fact that it's all about electrons, right? There's no E in oil rig, so. Okay, so Leo, what does that stand for?
Loss of electrons.
Losing electrons or loss of electrons, right? I can't spell this way, but that's fine. Lose electrons is oxidation. A gain of electrons, well, that's really hard for me to do, is reduction. And so if you write this down every single time, as long as you understand the idea of gaining and losing electrons, then this will be totally fine. We're going to keep that in the back of our mind to see if things are gaining or losing electrons here. And we're going to keep that in the back of our mind, and we're going to use that to define things as either oxidation or reduction. Any questions for now? We're going to learn about the oxidation state. Now, I need you to understand that this is the foundation of almost everything in this unit. Understanding oxidation numbers, day one of this unit, this is maybe the most critically important thing that we're going to do all unit, because it forms the foundation of everything else. Like, for example, can you learn how to multiply if you don't know how to add? No. Can you learn how to subtract if you don't know how to add? No, you can't. Okay? Everything builds off of this foundational principle. The oxidation state of an element is the apparent change that an atom would have, or charge, sorry, that an atom would have if all the electrons in a covalent bond belong to the more electronegative atom. That's a big statement, okay? But what I want you to think back to is in Chem 20, do you remember dealing with electronegativities? No. Yeah? No. No? What's the most electronegative atom or element that there is on the periodic table?
Oh, I remember.
Top,
Right.
fluorine. Not quite top right, but you know what I mean. So fluorine has an electronegativity of 4. Do you remember what the least electronegative thing on the element period? Yeah, we call it francium, even though technically it doesn't exist, right? Because it's a synthetic element. I mean, it does exist. Mr. Town would slap me if I said that, okay? But it exists after the core of a star goes supernova. You know what I mean? Like, you're never going to see francium. But anyways, whatever, that's fine. So in any bond, how many electrons make up one bond? Do you remember? 2 electrons make up one bond, okay? So let's draw water. Let's try this. Water is H2O. But let's draw this out a little bit more than it is kind of written here and now. I'm going to draw the Lewis structure for water. So bear in mind. Yes, Shohei, you do not have school on Friday. You have school on Thursday. But not Monday. You have a 4-day weekend coming up. I have a 3-day weekend, but you have a 4-day weekend. Okay. Let's think about this. Hydrogen and oxygen each share an electron, right? They're both kind of giving one electron to this bond. So here's that bond. But what I want to know is which one of these is more electronegative? Is the hydrogen or is the oxygen more electronegative?
Oxygen.
What's oxygen's electronegativity? 3.2, right? And what's hydrogen's electronegativity?
2.2.
I was going to say 2.2, right?
Oh, those
Yeah. So hydrogen's electronegativity is 2.2, oxygen's is 3.2. Remember, this bond is a tug of war, right? This atom and that atom, they're trying to pull these electrons one way or the other. Right now, who's kind of winning? Nobody totally wins, But who's kind of winning this tug of war?
Oxygen.
Oxygen. Oxygen has an electronegativity. Oxygen's electronegativity is 3.2, hydrogen's is 2.2. And so, if we wanted to, we could say that the oxygen is winning this battle. So, who do the electrons belong more to? Do they belong more to the oxygen, or do they belong more to the hydrogen?
Oxygen.
They belong more to the oxygen. So what does that mean? Did the oxygen they didn't actually steal any electrons, but did it pick up any electrons away from the hydrogen? This oxygen, if the electrons all now belong to the oxygen, how many extra electrons does it have now? It's got 2 extra electrons. Does that make sense? So the hydrogen, each hydrogen has lost an electron, and each oxygen has gained an electron. Really, there hasn't been any transfer. It's just that because oxygen is winning, we say, nah, oxygen won. We're just going to say that the electron was given to oxygen. So oxygen here, oxygen has 2 extra, in quotation, electrons. Because it's more electronegative, because it's winning the battle. Hydrogen has lost 1 electron each. Now they haven't actually won or lost any electrons. It's just that because one is winning more than the other, we just say, okay, it won. So what does that mean? What's the apparent charge on the oxygen now? If it was neutral before, right? If it was neutral before and it picked up 2 electrons, what's its apparent charge?
2 negative.
2 negative. Are we okay with that? Because we're just giving them to the oxygen. All we're doing is we're trying to just figure out, okay, who's got more of the electrons and who's got less of the electrons. So here we say oxygen has an oxidation number of -2. Hydrogen. If hydrogen oh, howdy. Sorry,
I didn't mean to interrupt you. I was just going to wave at you, but now you.
I was knee deep in thought, wasn't I?
Chem
Yes, sir.
30.
Chem 30.
How are you doing?
I'm well. How are you? Good.
Looks like a pretty good group here.
Oh, it's the best group.
Is it?
Yeah.
Who's the smartest in here?
Joseph.
His favorite student.
This guy right
Is
here.
he? That makes
Yeah.
sense. That's well played, by the way. Do you have
Yeah.
a test coming up? That's
No.
what I used to
No, they just brown nose.
do. That's how
all
I
over.
graduated.
Yeah.
Alright.
I hope he's okay with being on YouTube. So, anyways, hydrogen. Has hydrogen lost or gained any electrons here in this transaction? Has each hydrogen, let's look at this hydrogen, did it lose or gain any electrons?
Lost 1.
Theoretically, it lost 1. So what charge should it have?
1 positive.
1 positive. When you lose a negative, you become positive, right? So hydrogen now has an oxidation number of +1. Oxidation numbers and oxidation state mean the same thing. If I said it has an oxidation number of this or it has an oxidation state of this, it's the exact same thing. Okay, I mean they're totally synonymous. Now, oxidation or hydrogen has an oxidation number of +1, and oxygen has an oxidation number of -2. That's all we're doing is we're just saying, okay, one of these owns more of the electrons than the other. And then we're going to be able to use this idea to be able to keep track of, do things actually lose or actually gain electrons next?
Are there reduction?
No, we say oxidation numbers because some dude picked that word a long time ago.
Okay.
Yeah. Is that okay?
Yeah, thanks.
Yeah, no problem. Okay, there are some rules for oxidation numbers, for assigning oxidation numbers. We should be able to assign an oxidation number to any element in any compound ever. We should be able to do that. There's a bunch of rules. The oxidation number for ions is the ionic charge. Now let's see if that makes sense. I'm going to draw a picture of a sodium atom. Do you remember that this is the Lewis diagram for a sodium atom?
Yeah.
Yeah. And so it has one valence electron, right? When it turns into an ion, it loses one electron, right?
Yeah.
So we say that it's positive because it's lost an electron. Well, that's really close to the same idea as an oxidation number. The oxidation number is how many electrons does it have more or less than it should have, and sodium has one less than it should have. And so, okay, let's look at this. What's the charge on calcium 2 plus? 2 plus. So what's its oxidation number?
2.
2. 2 plus. We say plus 2. We try to differentiate between charges and oxidation numbers. Charges, the plus or minus should always go after the number. Oxidation states, the charge should always go before the number. It's not that big of a deal. It really isn't. I just don't want you to get confused. What's the oxidation state on a sodium 1 plus ion? 1 plus. So plus 1. We would say plus 1. And what's the oxidation state on a chloride ion? Negative 1. Was that hard? That was phenomenally hard. Okay, let's try the next rule. Oxidation numbers for elements or molecules are 0. Okay? What I mean by that is is P4, is that an element? Is there only one type of element inside there?
Yes.
Yes. Okay, I'm going to draw a picture of P4. And I don't think you'll be surprised that this is what P4 looks like. It's just one ring of P4. Now I'm going to trade each bond for some atoms, or for some electrons, sorry. No, I'm using orange and black because those are the only colors that I have available up at the front. Okay. Okay, what I'm trying to do is I'm trying to show you that this phosphorus, it donated this electron to this bond, this phosphorus donated that electron to that bond, this phosphorus donated that electron to that bond. Let's think about this. What's the electronegativity of phosphorus? Check it out. What's the electronegativity of phosphorus?
2.2.
What?
2.2.
2.2. So this is 2.2. What's the electronegativity of that phosphorus? 2.2. And what about that one? 2.2. And what about that one? So who's winning these tug of wars? Nobody. So basically everybody is splitting these bonds totally equally. Does that make sense? Everybody's just totally sharing, 100% sharing these bonds. So, has anybody lost or gained any electrons? No. That's because they have the exact same electronegativity. So if nobody's losing and if nobody's gaining, then what's the oxidation state? 0. In every element everywhere, if it's an element all by itself with no charge, it'll be 0. What's the oxidation number for chlorine inside Cl2? 0. And keep in mind, I'm referring specifically to one of the P's in P4. Okay? What's the oxidation state of 1P inside P4? What's the oxidation state of 1Cl and Cl2? What about zinc? 0. Is that hard? It's going to be putting all these rules together that's difficult. Okay, the oxidation state for hydrogen is +1 all the time, unless it's attached to a metal. Okay? Let's think about this. What's hydrogen's thingy? What's it? Electronegativity. 2.2. And what's lithium's electronegativity? So who's winning that tug of war? Hydrogen is. So hydrogen is going to be negative when it's with a metal, but it's going to be positive when it's with a non-metal. Is that okay? So hydrogen is -1 here, but it's +1 here.
I had tungsten, hydrogen. That would be negative.
You're never going to see that.
Okay.
Yeah. I want to be very clear. You're just never going to see complicated problems like that.
Okay.
Yeah. Okay.
No, I just
The oxidation number for oxygen is always -2 unless it's something that we call a peroxide. So again, this is another just like a weird random rule. A peroxide is like HOOH. Let's think about this. The oxygen is the oxygen beating out the hydrogen for its electron. Yes, but is the oxygen beating out the other oxygen for its electron? So how many electrons has this one oxygen won? How many has it been victorious over? 1, right? So they're each going to be -1. So it's a -1 there. But if we have an oxygen like double bonded to something, okay? We're going to say, oh yeah, here, sorry. The fluorine here, is it more electronegative than the oxygen? Yes, then it's -1. Okay, and oxygen's going to be +1, or -2, +2. But again, you're not going to see those. Let's see a more typical example of that. Let's see, like HOCl, something like that. The oxygen here, is it going to beat out the hydrogen? Is the oxygen going to beat out the chlorine? No?
Yes. That's 3.2.
Yeah. Woo. Okay. The oxygen beats out the chlorine, right? 3.4 to 3.2. So this oxygen is going to be -2. I want you to keep in mind, oxygen is always -2. Like in the vast majority of the examples, except for peroxides, which I don't think you'll ever see this year. I just have to tell you that. And except for bonded with oxygen, which I don't think you'll ever see, but I just have to tell you that. Is that okay? Oxygen is -2 all the time, and we'll.
Bonded with fluoride or?
If it's bonded with anything other than itself or fluorine,
Okay.
and so I just want to let you know you're never really going to see that kind of stuff. Okay. Now, the total sum, if you added up all of the oxidation states of everything inside something, it should be equal to the total charge on the whole thing. What's the total charge on this entire molecule? Do you see a charge written there? No, so it's 0, okay? So, oxygen, what's oxygen all the time? So it's -2. And there's 2 of them. Carbon we don't know yet. We'll get to that in a second. But the whole thing should be 0. When you add up all the when you add up all the oxidation. What's this whole thing? What's the charge on the whole thing? -1. So if you added up the 1 nitrogen plus the 3 oxygens, it should equal -1. Okay? I just need you to know that, and then we'll use this information later. What's the total charge on this entity? +1. So if you added up the 1 nitrogen and the 4 hydrogens, it would equal +1. And then in a molecule, the more electronegative atom is assigned the negative oxidation number, but we've been dealing with that this whole time. Let's use all these rules at the same time. Trust me, we will get used to this. Does anybody think that this is complicated but right now? Yeah. After the first 2 rules, was it complicated?
Yes.
A little bit? Okay, all right. So just keep in mind, the oxidation state of any ion is just ion charge. The oxidation state of any element is 0. Oxidation state of hydrogen is always +1. We're just going to assume it's always +1 unless it's a metal hydride. Oxygen is always -2, and then the charge on the entire entity is all of the oxidation states added up. Okay, I've got a little bit, this is your textbook. and it just sums that information up. Atoms and elements are 0. Hydrogen is +1. Oxygen is -2. All monoatomic ions, like sodium ion, is just a charge on the ion. Let's use that to find some things out. It says, what is the oxidation state of carbon in methane? Okay, let's try and go through this. Do you see any ions in here? No. Is this an element all by itself? No. But what's the charge on the entire thing? 0. The whole thing is 0. Is there anything in here that you know about? Did we learn any rules about carbon?
No.
Did we learn any rules about hydrogen?
Yes.
Hydrogen is always what?
1.
+1, and we don't know what carbon is. Okay? So if we have 1 carbon and we've got 4 hydrogens, what can you say about the carbon? The carbon's oxidation state has to be -4. Are we okay with that? Okay. So the carbon, it's got an oxidation state of -4. Perfect, no problem. What is the oxidation state of sulfur in something called sodium sulfate? Now, do you immediately know the formula for sodium sulfate? Kind of. This is this ionic or molecular? It's ionic. It's saying the name of this ion and the name of that ion, right? So let's think about this. Sodium is what? Na plus, and sulfate. What the hell is sulfate? I don't know. You tell me.
SO4 2 negative.
It's SO4 2 negative. You don't have your data book. It's in my bag. Oh. Okay. Sorry, is that disrespectful? Let's think about this. Sodium sulfate. Really what it's asking is what is the charge on the sulfur in a sulfate ion? Can you understand that? It's really not asking me about the charge of sulfur in sodium sulfate. It's really asking me what's the charge of sulfur in sulfate. Okay? Now let's do it both ways. Let's do it the way the question is intending for us to do it. What's the formula for sodium sulfate? How many NAs and how many SO4s?
Na2SO4.
Okay, Na2SO4. What is the total charge? What's the total charge of this thing? Total oxidation state? It's 0, right? This thing is neutral, so it's got to add up to be 0. How many sodiums are in this thing? 2. And what's the charge on each sodium? +1. So if we take 2 +1s and we add it to how many sulfurs? 1. But we don't know what it is, so I'm just going to put an S. And how many oxygens are in here?
4.
And what's the oxidation state of oxygen all the time? -2. This is basically just an algebra problem. This is just us trying to figure out, okay, well what does the S have to be if it all combined to be 0? So what's 2 pluses and 4 -2s? That's 2 plus S minus 8 equals 0. What does S have to be in order for everything to add up to be 0? Has to be +6, right? So the sulfur is +6. I hope you understand that if I ignored the sodium, and I just said sulfate, okay, I'm going to do this in red now. You don't have to write this down, but if you want to write it down, you can. Let's try and figure out what the sulfur in sulfate is. It's 1S plus 4 oxygens equals, what's the total charge on sulfate? 2 negative. We end up with the exact same problem. S minus 8 equals -2. And if I add 8 to both sides, I get S equals 6. So it doesn't matter which way you do it. If you're confused by me saying the question's really asking you what the sulfur and sulfate is, then that's fine. You can just do it as fine. Do you want to do some more examples, or do you want to try this out yourself? Let's do 2 more examples. Is that okay? We're going to do NF3, and we're going to do Cr2O72-, if that's okay with you. NF3, let's think about this for a second. What do you know about this substance? Does it have any ions in it? No. Is it an element? No. What can you say about the total oxidation state of the whole thing? They should all add up to be 0, right? So something's going to equal 0. It's because I've underlined nitrogen, it's saying figure out what the oxidation state of nitrogen is. Now what I want you to understand is fluorine going to win the pull for electrons in this tug of war? Fluorine will. It's the most electronegative. So each fluorine is going to be -1. Is that okay? Each fluorine is going to be -1. And you've got 3 of them. So what does the nitrogen have to be in order? +3. So the oxidation state of nitrogen in this example is +3. Okay. We didn't actually have to make up like some equation for that. We could have just said, well, this is -1, each of these is -1. If I have 3 -1s, I need 1 +3 to balance it out. Let's do the Cr in Cr2O72-. What can you say about this whole entity? It's ionic. It's an ion, right? And what is the charge on the ion? 2 negative. So everything has to be equal to -2. So let's go 2 Crs plus 7 oxygens. What's the oxidation state of an oxygen? -2 all the time. This is a really tough one. This is a really difficult example. Two CRs, and the oxygens are -14. Do you know what the chromium has to be? +6, right? Okay, I'm going to add 14 to both sides, so I get +12, and I'm going to divide by 2 to get +6. So the chromium has to be +6 because the oxygen is -2. Any questions about this? It's a little bit of math, but you can use your intuition as well, right? There are some shortcuts in here, for sure. There are big time shortcuts. For example, the aluminum hydrogen carbonate. What do you notice about aluminum hydrogen carbonate? This is an aluminum ion, and this is a hydrogen carbonate ion, right? So if you wanted to, you could just focus on the hydrogen carbonate. What's the charge on one hydrogen carbonate? What's the charge on one hydrogen carbonate ion? -1. So 1 hydrogen, 1 carbon, and 3 oxygens equals 1 -1, right? It's asking about the ion in an ionic compound. Any questions? Just go ahead and try it out. Yeah. Look for them. Boston, you doing okay, man? Logan, you had a question? What?
What do you have? That doesn't look like strawberry.
No, it's blueberry, mango, something. No, there's no plum there. Yeah. No, only if you don't know anything else about that substance. Okay, so let's go through our list. Are there any ions? No, because it's not an ion. Is it an element? Yes. Is it an element? No, it's not an element. What do you know about the total sum? If you added up all the oxidation states, it would equal 0. That's the thing. Okay, now, the only other rule is no oxidation. The only other rule because in that breed, the nitrogen is bond, and each of those bonds is so if the nitrogen has 3 electrons,
That's these would just be 0.
If you just don't understand how you guys are connected, you understand this one is 6.
yes, what do you know about this? Okay, so potassium, what's the charge of potassium?
Because I know,
If it's in a, I don't know, you can tell me.
like maybe there's. I just do the bond.
So what? Oxygen
Plus 6.
What do all of the oxygen?
Oh, I understand. You guys had 6 now.
All of them is
Plus 2.
oxygens, and you don't want to. It's an ionic compound. So what if it's Yeah. Well, the chlorine is winning everything. Hydrogen plus one. And the chlorine, because they're not such a the most electronegative, yeah, negative 3. Yeah.
Because of the
I'm good.
Thank you.
Okay, I'm gonna stop us, and I'm gonna put up the answers, but I'm gonna slowly show them to you, and I don't know how I'm gonna do this. I gotta like hit the next slide, and then I gotta hit the shade button really quick. Here we go. Bam, bam. Oh, boom. Look at that. Okay, when I look at this, are we okay with the sulfur in S8 being 0? It's an element. That's one of our first rules, right? Are we okay with the HPO4 2 minus, the P in there being positive 5? Okay, stop me if you want me to do any of this math.
What the heck? Hey, can you do like 4?
This one?
Yeah.
The HPO4 2 minus?
Love that.
Yes, I can. It depends on how well you do arithmetic in your head. Okay, the first thing I want to get you to start thinking about, what are all the oxidation states in the whole thing adding up to be? Okay, HPO4 2 minus. What are all the oxidation states going to add up to be? -2. They all have to add up to be -2. Now, how many hydrogens are there in HPO4? 1. So that's +1. And how many phosphoruses? Just 1, right? And how many oxygens are there? 4. So 4 -2s. So if we added this all up, 4 times -2 is -8. -8 plus 1. -8 plus 1 is -7. So what would you need -7 to give you -5? Add 7 to both sides. P equals +5. No, +2. What? I think I did. My brain was working faster than it should have been. So P equals +5. Woo!
You scared me.
Yeah, I scared a lot of people, I think. Any questions about that? I'm just assigning, what is oxygen always? -2. What is hydrogen always? +1. I will warn you if you ever see something that's not the case. Okay, in chromate, CrO4 2 minus, the chromium is going to be +6. In this, right, the whole HCO3 adds up to -1. If we have 1 hydrogen and 3 oxygens, that's -6 plus 1 is -5. Has to equal -1, so the carbon has to be +4. I'm going fast through this, but I'm going fast because I'm assuming you've already put in the work. The phosphorus in P2O5 is +5. The iodine in potassium hydrogen iodate, or whatever that is +7. Yeah, you want to do that one? Okay, let's do that. Okay, let's deal with the entire thing, right? Let's not split it up into this ion and that ion. Let's deal with the whole kit and caboodle. What do you know is the charge on the entire thing? 0, right? I don't see any charge here, so the whole thing is going to add up to be 0. Is this an ionic or a molecular compound? I should hear a chorus of either ionic or molecular. Ionic. What does it start with? K. Starts with a metal. So it's ionic, right? Yeah, shoot.
That's not the word I said.
Okay. Potassium. If potassium was an ion, what charge would it have? +1, and there's 2 of them, right? So 2 +1s. Plus, how many hydrogens do I have? How many hydrogens? 3, so 3 +1s. And I have an iodine, and I have 6 oxygens, right? So 6 -2s. Holy, this is going to be a lot of adding and subtracting. What's this here? positive 5 plus I minus 12 equals 0. So what has to add up? Like negative 12, this has to be positive 12, so that means I has to be positive 7, right? Is that okay? Or we could just move everything to the other side. Let's add 12 and subtract 5. So add 12. So 5 plus I equals 12. Subtract 5. Subtract 5. Like either way you work it out, as long as you do the math properly, then you're going to get the appropriate oxidation state. Yeah.
When did you start producing these?
When I was in grade 2, I think. I think in grade 2. Okay, I'm going to put up the other ones here. The carbon in CHCl3 is +2. The carbon in sucrose is 0. The lead in PbI4. Does anybody know where I got the positive 4 from PbI4?
Yeah, the 4 ion I take 4 electrons.
You can think of it two ways, right? Which one's more electronegative, the iodine or the lead? The iodine. So the iodine steals 4 electrons from the lead. Another way to think about this, is this ionic or molecular? It's ionic. It's made out of a lead 4 plus and 4 negative ones, Macy. The third one down on the right side, the AlHCO3 3. Okay. Let's try that. Can somebody close the door out there? They're doing a lab. Okay, Macy, this one's maybe the toughest one because there's so much going on here. The first thing I need you to ask yourselves, is this an ionic or a molecular compound? It's an ionic compound, right? It's an ionic compound. So, what do you know, Macy, what does the total charge on everything need to be? If you add up all the oxidation states, it's going to be 0, right? How many aluminums are in there? 1. And if it was an aluminum ion, it would have a charge of 3+, right? Okay, +3. And let's think about everything else. How many hydrogens are in here? 3 of them, right? Yeah, I know, but we're going to do it this way. 3 plus 1s. How many carbons are in here? 3, right? 3 carbons. And how many oxygens are in here? 9. Yeah. 9 negative 2s. So then, once we add all this up, what's 3 plus 3? Plus 6. This is minus 18 equals 0. And then you just got to solve for it, right? So that's negative 12, 3c equals positive 12c equals 4. Hopefully that's okay. You seem very, very excited about that. Okay, I intentionally gave you a bunch of really, really hard, crappy examples. That was the intention of this is to show you, okay, this is a little bit hard, and you need to work at it. And we will work at it. We will have a little bit of extra practice, and that's totally fine. But let's head back. Let's keep doing our thing right now, and let's move on. And we'll keep practicing oxidation numbers. Okay. Now we're getting to that modern definition of oxidation and reduction. If the oxidation number of an atom or ion changes, then we know electrons had to have been transferred. Does that make sense? If something had it started with an oxidation number of 0, and then it went to be -3 or something like that, then obviously electrons were either gained or lost by something. And that's the definition of redox. Anytime electrons are transferred, we have a redox reaction. What does redox stand for? Reduction, oxidation. Okay, we can identify if an oxidation or reduction reaction has occurred based on the change of oxidation state. So let's try this. Identify the elements oxidized and reduced in the combustion of coal. Do you know what coal is? Carbon. So when you take coal and you burn it in the presence of oxygen, what are you going to get? Yeah, you're going to get carbon dioxide. If we're assuming it's complete combustion. And you don't know what that is, so we will. Let's think about this. Let's look through the entire thing and let's assign some oxidation numbers here. Let's figure out what are some oxidation numbers of the elements inside these things. What's the oxidation state of the carbon over here?
0.
Are we okay that it's 0? It's an element all by itself, so it's 0. What's the oxidation state of the oxygen here?
0. Oh, it's 0.
It's 0, right? It would be -2 if it was in a compound, right? But it's 0. Now, what are the oxidation states of the carbon and the oxygen inside carbon dioxide? What's one of the oxygens in here?
-2.
-2. I will write the oxidation state of a single oxygen. Now, if the whole charge of the thing is 0, what does the oxidation state of the carbon have to be?
2.
This is what really screws people up. How many oxygens do we have? 2 groups of -2 should be balanced by a +4, right? If you need to do the math off to the side, if you need to go carbon plus 2 -2s equals 0 and figure out that carbon equals +4, that's fine. I got no problem with that. Let's think about this. What happened to the carbon when we burned it? What happened to its oxidation state?
It lost 4 electrons.
Did carbon gain or lose electrons?
Lost.
It lost electrons. So this thing here lost 4 electrons. What about the oxygen? I'm talking about one oxygen atom inside the oxygen molecule. It gained, this thing gained 2 electrons. Is this a redox reaction? Did you get a transfer of electrons? Yes. The moment you ever see that one oxidation number has changed for one element, boom, you know it's a redox reaction. As soon as something has either gained or lost electrons, you know the whole thing is a redox reaction. What I want to know now, carbon, because it lost electrons, did it get reduced or oxidized?
Loss is a Leo, so that's an oxidation.
So if we lost electrons, is that oxidation or reduction? Oxidation. So the carbon was oxidized. If we gained electrons, was that oxidation or reduction? It was reduced. Okay.
Got more time?
That was a lot of stuff. Let's don't be so lazy. Let's watch Polar Express.
Yes, please. I love that movie. That movie was great.
What? And a magic bullet.
You should do have a
Yeah. That's the kind of thing.
Do you have protein?
No. Just fruit yogurt. Okay. How are we doing right now? How's your brain power? Pretty low? How much do I charge per smoothie? $55.
I'm broke.
Yeah, can I just scratch for
Okay, let's try this. Identify the oxidation and reduction in the reaction of zinc metal with hydrochloric acid. Are we okay with this? We know that hydrochloric acid is really just H+ ions. Now we're moving away from hydronium because hydronium complicates things. In this unit, instead of saying an acid is hydronium, we're going to say an acid is H+, because otherwise we would always have this water molecule hanging around and it would complicate things. Is that okay? So, let's do this one. What's the oxidation state of zinc?
0.
What's the oxidation state of this thing? +1. Now, we would say it's 0, except it's an ion, right? It's not an element, it's an ion. Alicia, there's stuff in the blue bin if you want to pick it up. Okay, all right. What's the oxidation number of the zinc?
+2.
What's the oxidation number of the hydrogen here?
0.
It's all by itself with no charge, so it's 0. So the zinc, did the zinc gain electrons or did it lose electrons?
Oh, I meant lost.
I don't know, did it gain electrons or lose electrons?
Lost 2.
It lost 2 electrons, right? If I'm getting more positive and electrons are negative, I must have lost negatives to become more positive. So the zinc lost 2 electrons. And what about the hydrogen? Each of them what? Gained 1, right? Each of them gained 1 electron. And how many of them are there? 2. That's where the 2 electrons comes from. A gain of 1 electron. So what I want to know is what thing in here was oxidized and what thing in here was reduced.
Zinc was oxidized.
Was the zinc oxidized or reduced?
Yeah,
It was oxidized. That's oxidation. And that means that the hydrogen had to have been reduced. I want you to try one last.
Would you ask us to write a chemical reaction and then find out which one?
That's what I'm trying to get you to do right
Oh,
now.
okay.
Methane burns to make carbon dioxide and water vapor. I don't know why I said 4.
Yeah,
What'd you say?
You probably meant to say gas.
water's 4.
4.
Form.
I don't understand.
Form.
Water vapor, right? Doesn't matter. Do it anyways. I'm gonna walk around.
Formula for methane.
I don't know. You tell me, Madge. Right now, you don't.
Two carbon. So carbon has.
There's 2 waters.
So this each of these has carbon dioxide. No, yeah, +1.
Every time you write something.
+1. And there's 2 This has 0. This has -2.
-2,
And then this one will have +4.
Wait, no.
This one will have -2.
I don't know why.
Yeah, -1. Makes it 0. Because each one of these
has negative percentage.
Last time you went to zero.
Last time I went to
Yeah, but there's two.
Oh, same. What'd you get?
I got two scores.
I got it. Why would you want
Because he doesn't
Oil blizzards do like or turtle blizzard.
Wait, Smarties and blizzard. Smarties make flurry.
Smarties and flurry? Yeah. There's no way that's better than flurry.
What is it?
No way.
Flurries are actually better than blizzards.
That's all I got.
Okay. When you burn it, what does it have to react with?
Stop!
Bake, carbon dioxide, and water. Correct. The
All oxidative state continues. Milwaukee, Harris, Angel.
Just finish it.
No,
It's making me mad.
I know, it's good.
She doesn't have a shirt flavor.
Learning and how.
Okay, tomorrow we're gonna go over this practice, this problem, and do a lot of practice.
What's PAFU?
PAFU.
What's that?
PAFU.